Thanks very much, Nigel. So welcome to my talk. I will be talking about biomarkers in atmospheres. So biomarkers are molecules, species, which are indicative of life. Okay. So just a brief overview of what I'll be talking about. I'll be mentioning just a little bit about how diverse life is on our home world. I'll give a little bit a historical context of right the way back to antiquity, the so-called debate of whether there are many Earth-like worlds or not, whether life was originated on many planets or not. It's a very old debate. I'll describe some methods for detecting biomarkers. I'll talk a little bit about what we know about the chemistry of biomarkers. I'll talk about lessons learned from the solar system, and then finally, in the context of the new field of exoplanets, I'll talk about biomarkers beyond the solar system. So here's a slide which is like showing the diversity of life on Earth. So that there are some real sort of biggest, largest, oldest kind of life types, which is home to our planet. These are the redwoods in California. They're the largest living organisms on the Earth. This is an Antarctic sponge, which is one of the oldest organisms on Earth. They're up to 1,500 years old. So you have like a large diversity of scales in terms of age, in terms of size. These are bacteria. This is a virus. This strange creature actually, it's not a made-up picture. It's a real organism which lives on the bottom of the Earth. Here. These like monster-type creatures were around at the time of the Precambrian in our planet's history. So you can imagine. Oh, this guy, by the way, I wonder if you know who that is. I'll come back to him and show him in a more familiar form at the end of the lecture. But the point I want to make here is that life, even on our own planet, is very diverse. And so if we're in the business of trying to identify life on planets outside the Earth, then it's a very challenging thing to do. Yeah. The historical context is reduced into two schools of thought, which started in ancient Greece. The so-called atomist school lay claim to the atom being infinite in number, so therefore worlds which can be made up from the atom are also believed to be infinite in number, so an infinite number of Earths. This was held by the philosophers Democritus and Epicurus. Whereas the other school of thought, on the other hand, the Aristotelian school, held that a unique creator implies unique creation. So this is like the many worlds friendly point of view, the atomist school, and this is like there's only life on the Earth school. But the point here is that this debate has gone on for thousands of years. So this idea of plurality, many worlds with life or not many worlds with life. Here's just a brief overview of some famous astronomers and what their views on plurality were. So Galileo Galilei talks about life on the moon, and if there is life on the moon, it must be far beyond our imagining, he said. Kepler said that humankind is a predominant creature in the universe. Isaac Newton speculated that the fixed stars could be centers of other planetary-like systems. I imagine that this has been done before as part of the ABC lecture series, but I want to very briefly mention the so-called classic definition of the properties of life. So 1, 2, 3, 4, 5, 6, 7 properties here. You can see, so life is defined to exhibit homeostasis, so it regulates its own environment. It is split up into organized sections, the cell, for example. It exhibits a metabolism, so it breathes to obtain energy. It exhibits growth, it adapts to its environment, it reproduces, and it responds to external stimuli. Of course, the problem with this so-called classical definition is that it doesn't fit to, it's not exclusive. Fire, for example, grows. Crystals melt when it gets warmer, so you can argue that they adapt to their environment and they have their own internal organization. So based upon these simple 7 properties, then defining life in this way is not easy. The modern definition is based upon genetics in an evolutionary context. Okay, here are some definitions in the field of biomarkers. So in astrobiology, the word biomarker means a compound, as I said, which gives evidence of life being present. But in medicine, it is also used as a tracer to examine health. It also crops up in biology. A biomarker is a term where biology is involved in petroleum formation. The term biosignature, usually in atmospheric exoplanet literature, is synonymous with biomarker. So biomarker, biosignature are terms which give a very good indication, if we find them, of life being present. On the other hand, the term bioindicator, it's similar to biosignature and biomarker, except it's not as much evidence. So it means that if you find a bioindicator in a planet, it means maybe there's life there. It's a step on the way to possibly establishing that life is there, but you really need more evidence. For example, large quantities of oxygen alone may indicate life, but do not necessarily indicate life because there are inorganic means of forming oxygen. So now I'll move on to talk about the methods of finding biomarkers. So very broadly, the methods are split into in-situ methods, where you physically go somewhere and, for example, you stick something into soil or into rock and then analyze it, or remote methods, which of course are more interesting for exoplanets because we can't fly there anytime soon. So very briefly, the in-situ methods involve fossils. Of course, if you can see fossilized life, it's evidence of life being there. The number of carbon atoms in the sample is indicative of life. You can take spectra, and the spectral bands or combinations of spectral bands can indicate the presence of life. Life favors particular isotopic ratios, or it favors the use of particular isotopes of carbon, nitrogen, and oxygen, which can be used as a biomarker. And life has chiral properties, which I'll talk about briefly later on. So the remote methods are spectral methods. For example, vegetation has a particular spectral property, a steep gradient in the visible region, which I'll talk about briefly later. There are biomarker compounds in atmospheres. There are mineral spectral features, and also entropy. Disequilibrium of entropy can be used also to theorize the presence of life. So my main area of focus is remote biomarkers, but I'll just give a very brief overview of in-situ biomarkers. So here you can see stromatolites, which are fossilized features by aggregation in shallow sea areas. In the central plot here, you can see fossilized methanogens. These are methane-producing bacteria. On the right-hand side, you can see the so-called blue-green algae, the cyanobacteria, which produce oxygen. Right. Another form of in-situ biomarkers is the so-called carbon distribution. So you can see here the carbon number, the number of carbon atoms in a particular molecule, well, in mixtures of molecules. Sorry, so you have like a mixture of organic molecules here with C14 in, with C18, with C22, with C26, and this plot is showing the relative number of the different carbon molecules. So if you go to a laboratory and produce these molecules with like a chemical synthesis, then what you typically get, like in the top curve here, my mouse is gone. Oh, okay, is a smooth distribution. This is because chemical properties, they tend to vary linearly and smoothly between carbon numbers. So as you gradually increase the carbon number, you get an increase in chemical properties, which leads to a smooth transition or a smooth distribution in the number of carbon atoms contained in the different molecules. Okay. The bottom plot is showing the distribution of carbon number compounds in sheep's wool, and you can see that there are different. It's not a smooth transition. There are spikes. For example, there's a spike at C19, and there are 3 spikes at C26, C30, and C32. And the reason for this is that enzymes, which are used by life, are very specific, and they favor particular carbon compounds over other forms of carbon compounds for various functions. So if you can actually fly to a place where there's life away from Earth and make such an analysis, then the presence of such spikes could be an indication that life is present or was present on such a place. So this business, the idea of chirality. So what you're seeing in the plot here with the 2 hands are a carbon atom is in the center. Well, these are molecules. Okay, the carbon atom is tetrahedral, and there are different groups attached to the carbon atom. And if you have a molecule with a central carbon atom and with 4 different groups, then it has the property of being so-called handedness. So you have a right-handed form and a left-handed form, which are exactly mirror images of each other, and this property is called chirality. The strange thing about chirality is that chiral members, so the left-handed form and the right-handed form, have identical chemical properties. Nevertheless, life seems to favor one particular chiral form, and I mean, it's quite difficult to imagine why this is so, because as I say, they have exactly the same chemical properties and physical properties. One theory of how this could have come about is that the life precursors, amino acids, we know that they are present inside dust clouds, interstellar medium dust clouds, and also inside these dust clouds are magnetized grains of dust, which as light is passing through the dust cloud and forming the amino acids, it favors the formation of a particular type of chirality. And the idea, the theory here is that one particular form of chiral molecule got delivered to the Earth as a precursor to life and was used by life to develop, and therefore life form favors one particular chiral form. Another in-situ biomarker is the isotope ratio of a particular compound. So life in its metabolism favors a particular isotope of hydrogen, carbon, nitrogen, or sulfur. Why that is not very well understood, but enzyme reactions are sensitive to the type of isotope present, and they lead to isotopic biofractionation of isotopic signals. So I'm going to move on now to remote biomarkers. The first remote biomarker I'm going to talk about is so-called entropy production biomarker. So life on the Earth produces high entropy to maintain its order. I mean, life has very ordered structures and is associated with high entropy. The central Gibbs free energy equation is shown here. So my Gibbs free energy change is equal to my entropy change minus temperature times the entropy. So delta G is delta H minus T delta S. This is a central equation from chemical thermodynamics. But from a second definition of delta G, which is equal to the gas constant times temperature times the natural logarithm of the of K, the chemical equilibrium constant, it can be seen. Okay, this is quite a simple way of presenting it, but it shows the main message is that delta G via delta S, so entropy is linked in some way with the chemical equilibrium constant. So you can. So the argument here is that if you have an atmosphere with life compared to an atmosphere without life, then the atmosphere with life will be moved away to a different extent compared to a dead atmosphere from chemical equilibrium. The big caveat with this argument is that all atmospheres, to some extent, whether they have life or whether they don't have life, will be out of chemical equilibrium due to photochemistry or temperature differences, etc. This is an important remote biomarker. It's the so-called vegetation red edge. So what you're seeing here is the percentage reflectance of light. So on the y-axis and on the x-axis, you've got wavelength going in the visible from 400 here up to, so this is the visible up to red, 900, and further on up to 1800 nanometers. And the substance being considered here is vegetation, so like a leaf, essentially. And the main feature here is this sudden increase in reflectance at about 700 to 800 nanometers. Why this occurs, it's associated with vegetation regulating its own temperature. Essentially, it prevents the leaves and vegetation from overheating. If you're walking through a forest or a woods on a warm day and you put out your hand and touch a leaf, then it always seems cool to the touch, and it's because of this red edge effect. So if we can imagine you're lucky enough to I don't know, in 30, 40, 50 years to be in a situation where we have a planet outside the solar system where we believe maybe there's life there, then one possible criterion to look at is to measure a spectrum in this range here. And here we're seeing the Earth in two different configurations here for where only the Pacific Ocean is facing us, and here where the African savanna is facing us. So in this situation, we would expect, at least theoretically, to measure a red edge detection, and here we probably don't expect to measure it. The next remote atmospheric biomarker is a so-called chemical anomaly. So this is like a cartoon showing, well, actually what happened in the Earth's early atmosphere over time. So what you're seeing, so we've got abundance, chemical abundance on this axis, and time on the x-axis. And in Earth's atmosphere, what happened is that after the cyanobacteria developed, there was a lag for a while, but gradually oxygen in the atmosphere started to rise up to its present-day value of 21%. In Earth's early atmosphere, there were maybe during the Archean, like 3 billion years ago, there were large amounts of CO2 and CH4 in Earth's atmosphere. And the CH4 went down as oxygen went up because oxygen oxidizes CH4. What I want to emphasize with this plot is that if you look at the modern day values of oxygen and methane, actually these values are very difficult to explain without life being present on the Earth. And the reason for that is we have two types of organism. One of them, the cyanobacteria, produces oxygen, and the other one, the methanogenic bacteria, produces methane. If you were to suddenly remove all, if you would like did a magical experiment and you suddenly remove all the methanogens and all the cyanobacteria from the Earth, then what would happen is that the Earth's atmosphere, the concentrations of these two compounds would change quite quickly, because they would react with each other, and the oxygen would quickly oxidize just about all of the methane in Earth's atmosphere to CO2. So the fact that we have present reasonably considerable amounts of methane and large amounts of oxygen in Earth's atmosphere, the fact that these two are present simultaneously, these two inconsistent with each other compounds, can be used as a biomarker. So here's an overview of the various types of atmospheric species which have come into the literature as biomarkers, along with their sources. So oxygen and therefore ozone are used as biomarkers. So oxygen mainly on the Earth comes from photosynthesis. Ozone is produced from oxygen. Nitrous oxide, this is the gas. It's called laughing gas. It was maybe, these days I don't know, but certainly in Britain 20 years ago, this was the gas that you had to knock you out when you went to the dentist to get your teeth taken out. It's N2O. It's an analgesic. It sends you to sleep. And on the Earth, it's a biomarker because it's produced, 99-point-something% of it is, of all N2O produced in Earth's atmosphere, comes from bacteria. So it's like a biomarker for bacteria, if you like. Chloromethane, CH3Cl, is produced by vegetation. So, for example, seaweed on the Earth, when the tide goes out, to prevent itself from drying, it emits various compounds. It's called to prevent desiccation, and chloromethane is also emitted as part of the anti-desiccation process. Carbonosulfide, COS, is also emitted by vegetation, and methane. Most of the methane on the Earth, maybe 90% of the methane sources on Earth, arise due to biological sources, due to methanogenic bacteria. I mean, this is all very well and good. Here you have like 1, 2, 3, 4, 5, 6 compounds, and I say, okay, they can be used as biomarkers. But I mean, the story is obviously a little bit more difficult, because all of these compounds, they aren't exclusively produced by life. Okay, maybe N2O is produced, 99.9% of N2O is produced by life, and in that sense, it's a very good biomarker. But the others, they are not all exclusively produced by life. So the game then is to try to understand the conditions of how much of these compounds are produced by life, and whether particular combinations of these compounds can be used to get like a better criterion for establishing life. So here's just the central photosynthesis respiration equation. So this is just saying that H2O and CO2 come together. I've written it in a very simple way. So CH2O means organic material. And what you see here, that oxygen is like a byproduct of this equation. Interestingly, what you see here is that the Forwards reaction producing organic material is almost completely balanced. So when the compound dies, then it rots, and the organic material is returned into H2O and CO2 mostly. How the oxygen gets into the atmosphere, I mean, if we only had photosynthesis and respiration, then it would be a complete balance and no oxygen would come into the atmosphere from photosynthesis. Okay, so the question is, how does oxygen get into the atmosphere? What happens is that this organic material, when compounds or when for example, when small creatures die in the ocean, they die and they sink to the bottom of the ocean, and their organic material, this CH2O, is removed into the bed of the ocean. It's called burial, and they end up going down via geological processes into the mantle of the Earth. And what that means is that this equation then is pushed away from equilibrium. What happens is that your CH2O is removed by burial out of the system, and that leaves behind the O2, which at the bottom of the ocean, O2 is not very soluble in water, and it simply bubbles to the top of the ocean and comes into the atmosphere. So you see an example here of the biomarker oxygen, or oxygen in our atmosphere. The amounts of oxygen are being controlled by a geological process, in this case burial. Oxygen is removed by reacting with reducing gases in the atmosphere, and it's removed by weathering processes, so reaction on surfaces like rock surfaces. There have been investigations in the literature as to what, if you like, is the best biomarker, oxygen or ozone. I mean, in a way, oxygen is the direct biomarker. I mean, photosynthesis produces oxygen, so if you can measure a large amount of oxygen, then it's the direct way of establishing at least a bioindicator. The problem with that approach is that if you're measuring spectrally, then oxygen doesn't really have very strong spectral features. What you can do to get around this problem is to use the fact that, as far as we know on Earth, the ozone layer is produced almost exclusively from oxygen. So if we didn't have large amounts of oxygen in the Earth's atmosphere, then we wouldn't have an ozone layer, is the argument here. So you can use ozone as an indirect proxy for an oxygen biomarker. And the advantage of doing that is that ozone has quite strong, or much stronger than oxygen, spectral features. What you're seeing here is a study by Antigone Segura in astrobiology, and you're seeing the ozone number density in ozone molecules per cubic centimeter against altitude. What she does is she takes like the Earth's atmosphere, assumes the Earth's development and the Earth's biomass at the surface, and then what she has done in this study is to gradually reduce the oxygen amount. So you can see, so the red line, PAL, is present atmospheric level. So the red line is the present amount of oxygen, and then the green line is oxygen reduced by a factor of 10, then blue by a factor of 100, and purple by a factor of 1,000. And what's being plotted is the change in ozone. So I'm reducing oxygen and plotting the change in ozone here. And you can see that maybe if you look at here, this region, the red line, the green line, and the blue line are staying approximately constant here. So I won't go into the details, but we know why this occurs. There are chemical feedbacks taking place in the atmosphere, which, even though you reduce your oxygen, then you preserve your ozone levels. So again, this is an indication that ozone is a really good biomarker, because for a wide range of oxygen, we still see the ozone signal. On the right-hand side here, you're seeing a theoretical spectrum. So 9.6 microns is the ozone fundamental band. So you're seeing here the ozone spectral feature for the various scenarios. So again, you can see that for one present atmospheric level and reduced by a factor of 10 and by a factor of 100, the ozone band is clearly visible. So this is an indication that ozone is a good biomarker. So here's a little bit of information about the Earth's ozone layer. You're seeing here, this is a two-dimensional plot where it results from a two-dimensional model. So the x-axis is showing latitude from the South Pole on the left-hand side to the North Pole on the right-hand side. And the colored feature here is the Earth's ozone layer. So red means 9 parts per million of ozone, which is not very much, but it's enough to protect us from the nasty UV. And it peaks at about 30 kilometers. So we're seeing here, this is like the heart of the ozone layer, this feature here. In very simplistic terms, one can talk about so-called good ozone. So good ozone is up in the stratosphere, which is good because it protects us from UV. It absorbs the UVB, for example. Whereas near the surface, one can talk about so-called bad ozone. This is also known as smog ozone. In fact, there are two different ways of forming ozone. The good ozone is formed in a different way to the bad ozone. I won't go into details about that, but I mean, ozone. If ozone is close to the surface, like here, the bad ozone, then it's a respiratory irritant, so it's not good for people with breathing problems or people with asthma. Okay. So just a little bit of information about the chemistry of ozone, how it's formed. So this is a one-dimensional ozone profile. It's essentially showing similar information as the 2D plot I just showed, but we're seeing here a profile. So again, here's the ozone layer peak at 30 kilometers, so 9 parts per million, 9 times 10 to the minus 6. So here's the mechanism by which good ozone is formed. So it's quite simple. Oxygen is split by radiation around 180 nanometers into 2 oxygen atoms, and then one of the oxygen atoms goes back and reacts with an oxygen molecule to form ozone. So it's a 2-step process. Low down in the atmosphere, the bad ozone, the smog ozone, is formed by oxidation of, for example, carbon monoxide. So you're seeing the central equation. So carbon monoxide reacts with 2 oxygen molecules to form an ozone plus a CO2 molecule. So those are the 2 ways of forming ozone. Of course, there are also, if you want to model ozone in Earth's atmosphere with an atmospheric model, then you also have to include reactions which destroy ozone if you want to reproduce the ozone concentration properly. And essentially, what's important here for destroying ozone are nitrogen reactions, which take place in the lower stratosphere at about 20 kilometers, and the well-known chlorine reactions. So the CFCs and the chlorine in the ozone hole, those are associated with chlorine reactions, which take place at about 40 kilometers and destroy ozone. So I'll move on to the nitrous oxide biomarker in Earth's atmosphere. So nitrous oxide is associated with denitrifying and nitrifying bacteria. So, for example, in Earth's soil, nitrogen from the atmosphere is fixed and comes into the respiration cycle, the nitrogen cycle. During the denitrification process, N2O is emitted as a waste byproduct. So it's associated with bacteria in the nitrogen cycle. If you quantify the sources of N2O and you put them into an atmospheric model and you look at like how big is my N2O biological source compared to, there are some reactions in the atmosphere which which are not associated with life, but which form N2O. And if you compare like the life sources with the non-life sources, then the life sources are like 1 billion times stronger at the surface than the non-biological. So in this sense, yeah, N2O is a very good biomarker. It's almost exclusively produced by life. As I mentioned, there are different criteria for biomarker. It's maybe not enough that it's very biologically specific. I mean, you also have to be able to measure it. For example, an exoplanet. So even though it's very specific for biology on the one hand, if it doesn't have a band or it has a very weak band which can't be measured, then it's also not much help for you. And in fact, N2O doesn't really have a very strong band. But the good thing about it is it's very biologically specific. Yeah. So during the study of Earth-like planets, so an Earth-like planet, well, is exactly what it says it is, applied to exoplanet science. The early Earth is used as a proxy for essentially we study the atmosphere of the early Earth and use it to try to make predictions or to learn or to discuss what we expect Earth-like planets, which would be discovered in the future, how their atmospheres will look. So there was a period on the early Earth called the Canfield Ocean, where Roger Buick expounded this idea in 2007 that oceans on the early Earth were very, very strong emitters of N2O due to strong bacterial activity. I did a study of these effects. This is a modeling study of an atmospheric model where I vary the N2O sources. So I'm basically increasing sources at the surface of N2O. I'm simply pumping more N2O into the early Earth atmosphere here. And what I found from this study is that that ozone in the model decreases. I don't want to go into the details of why this is here, but I said that earlier that when I talked about ozone, that nitrogen reactions were important for destroying ozone, and in fact it is exactly these reactions which are starting to become faster. As I increase the N2O, the nitrogen chemistry gets faster and the ozone decreases. But what was interesting from this study is that you come to a regime where the ozone stabilizes. So in terms of biomarkers and Earth-like exoplanets, this is kind of saying that even I can imagine different Earth-like planets with large emissions of N2O, but I'd still expect there to be an ozone signal. I'm not going to go into the details of why ozone stabilizes. You can look at the paper if you want to look at the chemical feedbacks. The main message of this plot is that the two central biomarkers, N2O and ozone, interact with each other chemically. Yeah. I'm going to talk about caveats now associated with biomarkers. This word red herring, or phrase red herring in English, it means something which can be a false friend, so it can put you on the false path, or it can indicate something which is not true. So that's why there's a red fish here. So a so-called false positive is used to describe a situation where we make our measurements for a particular planet and we conclude from our analysis falsely that life is present. Okay? So why would that be? Well, for example, one can imagine CO2 dominated atmospheres or steam atmospheres, where what happens is that these molecules photolize, and they photolize into, well, they release atomic oxygen, and the atomic oxygen can react with itself to form molecular oxygen. So in these cases, if we were to measure a large signal of atomic oxygen, and we may think, oh wow, look, here's a planet where photosynthesis is happening, we've got 20% oxygen, there must be life there, but it's false because the oxygen is produced by purely non-life processes, by photolysis of CO2, for example. Okay. So with this in mind, Frank Celsis, in his 2002 paper, discussed the concept of combinations of biomarkers. So the idea here is to think intelligently about which combinations of biomarkers would we really expect life to be present based upon our knowledge of the chemistry and the physics there. Okay, it's called the triple signature argument. So here's a possible false positive for N2O. I said this is a very biological specific biomarker. It's really almost exclusively formed by life, but nevertheless there is one or two reactions, or a few reactions, which form N2O abiotically, so without life. And here you see molecular nitrogen plus O forms N2O. And well, probably very slow is an underestimate. I mean, it is very slow compared to biology. I mean, it would be nice to have improved kinetic data. So chloromethane is the next biomarker. This is the vegetation biomarker for the seaweed that I mentioned. And there are reactions which have been established involving the reaction between methane and molecular chlorine, which form chloromethane. So this is only a false positive if the CH4 and the Cl2 come from non-life. Yeah. So if CH4 comes from outgassing or serpentization, and Cl2 comes from volcanic emissions, and they form CH3Cl by this reaction, then it's a non-life formed compound. Yeah. So methane is rather a problematic biomarker in my opinion. I said that on Earth maybe 90% of the methane sources at the surface come from life-associated processes, and about maybe 5 to 10% come from geological emissions. What you see on the left-hand side here, there's still a continuing debate about the presence of methane on Mars or not. In fact, these numbers here, like tens of parts per billion, have been revised downwards. Maybe if methane is there at all, there's a few parts per billion on Mars. There are all sorts of problems, like removing, if you measure methane on Mars from the Earth, then you have to subtract the telluric lines, etc. And it's very challenging, in my opinion. Also, if methane is present on Mars, then we really don't understand its photochemical lifetime. There are sinks of methane on Mars which we just don't understand at all. This plot is a pie chart which shows the various different sources of methane on the Earth. So you have like natural occurrences and anthropogenic, so man-made influences shown here. So you have like cows and rice paddies and biomass burning, etc. So I've talked about false positives. There also exists this concept of the false negative. So false negative means that life is there on a planet, but we don't see it, either because it's hidden. For example, the atmosphere is signals in the atmosphere are hidden by thick clouds, or the biomarker bands that we want to measure are just difficult to see because they've been interfered by other overlapping absorption bands, etc. It's always nice to, if you're in the exoplanet business and the Earth-like exoplanet business, to learn as much as you can from atmospheres in the solar system, where we have at least measurements of the composition. So this is like a slide showing learning from Mars in a biomarker context. So in Mars's atmosphere, oxygen and ozone abundances have been measured. And I can imagine two cases here. What you have on Mars is I don't know exactly 95% CO2. It's a CO2-dominated atmosphere. What happens in CO2-dominated atmospheres is the CO2 over a period of thousands of years, a bar of CO2 in maybe 10,000 years can photolize, and it would photolize into CO plus O. What happens then is the O can react with itself to form oxygen, and this is the false positive case that I mentioned. So if this were the only process, then oxygen would build up to quite large levels, maybe 20% or more in such atmospheres. Okay. Sorry, this is not a 95% case. This is a hypothetical case. It's a Mars-like atmosphere with 100% CO2. Okay, so there are no trace compounds in this atmosphere. It's pure CO2. And what happens is the CO2 would photolize into CO plus O, and the O would form O2, and it would be a false positive. The backwards reaction between CO and O is a very slow reaction. It's quantumly spin forbidden. And it's very, very, very slow, and it's never enough to, if you like, regenerate your CO2 atmosphere. So what we expect to happen in this case is that such a CO2 atmosphere would relatively quickly, in terms of geological timescales, would decay into CO plus O2. Okay. Case 2 is a Mars atmosphere. So Mars is almost 100% CO2. It's something like 95% CO2, but it has special types of catalysts in its atmosphere. It has hydrogen oxide, so the X just means different types of hydrogen oxide species, so like HO or HO2, etc., and also the same for nitrogen oxide species. What that means, it's actually very important for the stability of Mars's atmosphere, because if you look at the case 2 box here, so again, you have CO2 photolyzing into CO plus O, but unlike case 1, what can happen in case 2 is that the blue compounds, the HOX and NOx compounds, can regenerate the CO2. So they help to catalyze the reformation of CO2 from CO plus O. And that's important because it stabilizes Mars's atmosphere, and it doesn't lead to the O2 false positive. So in terms of, imagine on the Earth we want to measure such biosignals on a Mars-like exoplanet, then in order to distinguish between a false positive, case 1, and a Mars-like case 2, then you would need to know more information. You need to know measurements of, for example, water in the atmosphere to try to decide whether they're going to be catalytic cycles or not. Okay. So a similar plot for Venus now. So Venus, there's much less oxygen in Venus's atmosphere. We've recently measured a thin ozone layer at 100 kilometers in Venus's atmosphere. So, I mean, these are biomarkers of life, but I mean, ozone, for example, has also been measured on Venus, which kind of highlights that you have to be important when interpreting biomarker signals. You have to be careful, sorry. So again, case 1 on Venus is this case where O2 is formed eventually from CO2 photolysis. The second box, case 2, earlier in Venus's history, it is believed that there existed quite a thick water atmosphere. So what would happen with a thick water atmosphere is that water would photolyze into OH plus O, and again the O would react with itself and form O2. So it's sort of comparable, or it's similar to the case 1 here, that you get O2 as a false positive. But what actually happens on Venus is you also have the nitrogen and the hydrogen compounds, like on Mars. On Venus, you also have chlorine compounds, and these all together form catalytic cycles which regenerate your thick CO2 atmosphere on Venus. I'm going to talk a little bit about the literature of Earth-like atmosphere. So an Earth-like atmosphere means basically I start with the Earth, I start with what we know, which means I assume an atmosphere like the Earth, so an N2O2 dominated atmosphere. I assume the Earth's development, and I assume the Earth's biomass. So I assume emissions of biomarkers like N2O and methane at the surface in similar amounts to the Earth. And I'll just talk a little bit about some of the studies that have been done. So Earthshine is really a study of the Earth. So this refers to light from the sun being reflected from the Earth, going to the moon and coming back to Earth, where we can measure it and take up a spectrum. And we can use studies of these spectra to, it's like a real case in hand of a real Earth-like atmosphere, what a spectrum looks like, what we can do, what are our limitations, what are the challenges, which can be used like as a stepping stone to Earth-like exoplanets. There are a whole series of model studies called, I've called them moving the Earth in inverted commas. So as I say, these assume Earth's development and biomass in an atmospheric model. And then what they do is they imagine that, well, essentially they say that imagine the Earth is not like 93 million miles from the sun, but they move it like 10% towards the sun or 10% away from the sun. And then they let the atmosphere respond. So the atmospheric chemistry and the radiative transfer in the model will respond and will give you new atmospheric profiles of biomarkers and new temperatures. And then you can use these results to calculate theoretical spectra. So you have like an idea of if I were to have an Earth-like planet around a particular star or in a slightly different orbit to the Earth, then you get an idea of like a sensitivity study of how the spectral bands may change. As I say, the early Earth is used as like a proxy of what Earth-like exoplanets may look like. So Lisa Kaltenegger has done a study calculating spectra for different epochs during Earth's history and discussed these effects. Just a small word at the bottom here about Titan, because rather recently there's been a discussion about whether there are biomarkers on Titan. There were some results from Cassini coupled with modeling studies which suggested that the concentrations of C2H2 and H2 on Titan were lower than expected. And Chris McKay from NASA suggested that this may be due to a methanogen type bacterial metabolism. And the central metabolic equation is so the bacteria would from CO2 would take up H2 and produce methane as a byproduct. But I think the ideas are rather speculative. So well, I guess watch this space. So moving a little bit beyond the solar system now, so these are the type of like studies that have been done in the context of Earth-like exoplanets. As I say, we've looked at the early Earth. This concept of the Superearth, this refers to planets which have up to 10 Earth masses. There have been studies of so-called water worlds, so planets without continents, jungle worlds, so-called snowball Earth. There have been snowball Earth several times in Earth's history. At the start of the Proterozoic era, for example, the entire Earth was covered by an ice layer, etc. So the approach that is typically used is to vary boundary parameters in an atmospheric model, which is set up for Earth conditions. So you take your Earth model, then you change boundary parameters such as the central star spectrum, the age of the star, so the stars change their luminosity with age. You can vary the planetary outgassing rates, the protection from the magnetosphere. You can, if you have a model which includes escape at the top of your atmosphere, you can vary your escape rates. If a planet has active tectonics, then this interacts with atmospheres due to volcanic outgassing and weathering processes, etc. To kind of finish off this series of slides, I will talk a little bit about some specific studies. So here you see like a cartoon of like a typical M-Dwarf star, and here's your Earth-like planet here. M-Dwarf stars are very small, well, relatively small compared to the Sun, and they're cool stars. There's 3,200, 300 Kelvin, so much cooler than the Sun, which means that they're so-called habitable zones, so the region around the star where liquid water can exist, which favors life, is a lot closer to the star compared to Earth. So if the Earth is at a distance of 1.0 astronomical units, then a typical habitable zone around an M-Dwarf is, well, a factor of 8 or so closer. So why these are interesting to study is that one of the problems in identifying and characterizing Earth-like planets is the fact that the so-called contrast ratio, so the ratio of the brightness of the planet to the star, the planet is not very bright compared to big bright stars like the Sun. But for the case shown here, the M-Dwarf stars, then the contrast ratio is a lot more favorable because the star is smaller and less bright. So that's a good reason to study these systems and to look for Earth-like planets in these systems. That's the good. That's the advantage, but there are some disadvantages. And at these very close distances, the planet becomes tidally locked, which means that it has a constant day side to the star and a constant night side. So whether it remains habitable is then debatable. And if it's tidally locked, then its rotational rate will slow down, and that could mean that its planetary protection from the magnetosphere is a lot weaker. And if the planetary protection is weaker, and if it's close to the star in any case, then you expect a high cosmic ray input into such a planet. So the question here is that even though these are interesting objects in terms of like contrast ratios, there could be real problems for habitability if they're tidally locked and if they're flooded with cosmic rays into the atmosphere. So there have been some studies of these systems. Heike Rauer in 2011. Here's the central stars that she used. So she took the Earth and moved it to like a whole range of M-Dwarf central stars. So the M0, as the number increases, M means M star, and the spectral class number here, as the number increases, the star gets cooler. So they get smaller and more cool. So she studied M0, 3,800 Kelvin. Ardileo is an active star, M star, and M7 is the coolest star that was studied in this paper. And she assumed an Earth-like development, and she looked at Earth masses and 10 Earth masses, so the Superearth case. So here's a key result from that paper. So what you're seeing here is the brightness ratio, so the brightness of the planet to the star. And you see generally that these values are quite small, which is to be expected. I mean, for the Earth, the brightness of the Earth averaged over the Earth's surface compared to the Sun is of the order, I don't know, 5 times 10 to the minus 7 here. So this band is the the ozone fundamental band at 9.6. So this is the ozone biomarker for Earth. And what you're seeing here as the spectral class increases, so what's happening here is we are moving to, as you're moving upwards from the Earth to the green line, the red line, and the blue line, the star is getting smaller and less bright. So that means that the relative ratio of planet to star is increasing. Yeah. So planet divided by star, if the star is getting dimmer, means that the ratio increases. But you see a second effect. So the first effect is the contrast ratio is increasing. This is why we're so interested in these systems, because it's much easier to measure, to detect the contrast ratio for such a planet. If you look for M7, for example, it's moved up by, I don't know, a factor of 100 or more compared with the Earth. But what came out of this study is a second effect. You see that, for example, the M5 case and the M7 case, that the ozone band is slowly disappearing. And the reason for that is that this study includes interactive photochemistry and radiative transfer, climate effects. And what's happening is that as the luminosity of the central star increases, then the production rates, the chemical production of ozone, which needs UV for ozone to form, is being reduced, and it ends up with ozone concentrations decreased by so much that you don't see the band anymore. So that's the results of this study. So two effects: favorable contrast, but you have to be careful with if you can see ozone at all, if the chemical production gets switched off. This is a study that I did. So this is also looking at Earth-like planets around M-Dwarfs. I said that there could be problems if these planets, if the atmospheres are flooded with high levels of cosmic rays, and I've looked at this effect in this paper. So the plot on the left here is showing the chemical perturbation effect of cosmic rays. What I mean by that is that in an Earth-like atmosphere, one of the central effects of cosmic rays is they flood into the atmosphere and they break up the strong N2 molecule, and they split it into N plus N, into two nitrogen atoms. Here. Because there's also lots of oxygen in the Earth's atmosphere, the nitrogen atoms react very quickly and eventually form nitrogen monoxide, NO. And this is almost, if you will, like a proxy. NO production is like a proxy of cosmic ray intensity. So you're seeing here different scenarios. So you're seeing the logarithm of NO production from your cosmic rays. So a value of 2 means 100 NO molecules produced per cubic centimeter per second. And you're seeing 4 different cases. So for the Earth, for galactic cosmic rays, you see the values quite low. And then you're seeing increasing by step different types of M-star. So from a quiet M-star to a so-called active M-star, to there are certain M-stars which have severe flaring, which is the absolute upper limit for M-star activity. So this is like the upper limit, and you can see that the NO production goes up by a lot, by a factor of, I don't know, for the Earth you have 10 to the 2, up to 10 to the 6, so a factor of 10,000 of NO production. And this actually affects your biomarkers. This perturbs your chemistry. I mentioned earlier that nitrogen compounds can destroy ozone. And what you're seeing, I'll just focus on the ozone plot here. You're seeing the same 4 scenarios. So Earth, quiet M-star, active M-star, flaring M-star for the ozone column. So this is the amount, if you add up the amount of ozone throughout the atmospheric column, then this is a measure of total ozone column. And what you see is, for the ozone case, the bar on the right-hand side here, the flaring case, that there's so much NO being produced by the cosmic rays that it destroys your ozone biomarker. And you can see this also in the theoretical spectrum here. So this is the ozone fundamental for the quiet case. So you can see there's an ozone band. So the continuous line is the quiet star, and the flaring star is the dashed line. You can see here that the ozone band disappears. So I'm almost finished. So just a quick summary. So I've shown you a whole range of biomarker criteria, in situ and remote biomarkers. And I hope that I've convinced you that if you really want to establish life remotely, then you should try to apply as many biomarker criteria as possible, to use them together to try to come up with the best prediction possible. So we use atmospheric models with coupled photochemistry and radiative transfer to do these calculations, and it's always nice well, there are always ways of improving the models, for example, via more accurate input stellar spectra, better photochemical kinetics, more accurate radiative transfer, etc. Future work, which discussions are already underway here in Berlin, is to couple the atmospheric models with colleagues from other areas, including like a self-consistent treatment of atmospheres with outgassing from volcanic emissions at the bottom boundary of the model, and at the top boundary to include escape processes, so atmospheres can escape into space. So here's my last slide. So it's showing again the slide which I started off with, diversity of life on Earth, and maybe some of you guessed that the guy that I showed, the 14-year-old, was Albert Einstein. So okay, that's it. Thank you for your attention. So I guess I'll move to questions now.
Thanks a lot. We have 2 questions. So first,
hi Eva.
I pass Adam.
Thank you very much for a very nice lecture. And I have a question about the planets which are tidally locked by a star.
Yeah.
Is it possible that, for example, life can exist on the side which is protected from the radiation of the star? And, for example, the mixing in atmosphere can level the temperature on some approvable level, sorry.
Yeah, these are key questions which are being debated in the literature. The name of the game is whether the atmosphere on a tightly locked planet can be able to redistribute the excess heat on the light side into the dark side, and that depends on the atmospheric mass and maybe on how quickly the planet is rotating and on the Coriolis.
I'm sorry, I don't hear you. There are some disturbance. Maybe you are too close to your mic.
Can you hear me now? Is it better?
Yes.
Okay, so these are issues, tightly locked planets, which are being discussed, debated in the literature. The important point is whether the atmosphere of the planet is able to transfer the excess energy from the day side into the night side. If the atmosphere is too thin, then what may happen is that on the day side that it will get so hot that the atmosphere will vaporize, whereas on the night side the atmosphere will condense onto the ground. There have been some 3D studies with 3D models by Joshi et al. Which have suggested that most atmospheres will be able to transfer the heat from the hot side into the dark side, which should be helpful for habitability. But yes, you're right. If you want to get away from the nasty stellar cosmic rays, then you really want to be on the night side. Yeah. Okay. Does that answer your question? Or?
Thank you.
Okay.
Okay, so we have another question, this time from Eva Shushkevich. So I give you the floor.
Thanks a lot. Hi, Lee.
Hi.
Thanks for very interesting talk.
Thank you.
Really challenging. I would like to ask a simple question about the really things which we know very well. So the Earth is still the best, standard we can compare with, because this is where the life really was discovered. We have quite a lot of observations of the spectra coming from the Earth. And what are the most robust features which we can see in the spectra, and how well they are reproduced in the most advanced models today?
That's a very good question. It's not so easy to answer. There are different criterion. In terms of robustness, in terms of like, I see a really big band, and I know it's associated with a particular molecule. I'd probably say that ozone is the most robust. It's of the biomarkers. It has a strong spectral absorption feature at 9.6 microns. But whether that's enough to tell you that life is present it's probably not enough. I don't think, if I were honest, that there's one particular feature which I'd say we should focus on. I think we should focus on a whole spectra of investigating all biomarkers until we know more about them. Before we should really focus on one particular property.
Lee, can I interrupt you for a second? Can you put yourself in the middle of the camera and not speak so close to the microphone? Thanks.
Yeah, sorry.
Okay, thanks a lot. And can you remind me if N2O is well visible in the spectra of our Earth?
For the modern Earth, N2O is not so well visible. For the early Earth, it may have been the spectral band was probably larger because the concentration was probably larger due to the Canfield Ocean. What happens for Earth-like planets in the habitable zone of M-Dwarfs, N2O may well be higher in concentration because the UV is lower and it's destroyed a lot more slowly. So it may be higher, but for the modern Earth, it's certainly not very strong.
Okay, great. Thanks a lot.
You're welcome.
Okay, so we have no more questions. I guess that the weather in Berlin is like here, so have a nice evening despite the weather. And so thank you very much for the nice lecture, and see you in 14 days. Bye.
Yep. Yeah, thank you very much. Pleasure. Bye-bye.
Thank you. I would like to ask you to speculate a little bit on the question of the probability of oxygen or ozone being available on any exoplanet, considering that oxygenic photosynthesis is a very complex process and has been produced on Earth only once. So it is not that easy or given a property of any biosphere to invent oxygenic photosynthesis. So what is the likelihood of production of oxygen in a biosphere?
It's a good question. It's difficult to speculate. I'm not a biologist. I'm a chemist. Biologists tell me, as you say, that in terms of exoplanets, it's certainly more imaginable that there could be a lot more so-called worlds where there's life, but it's like a low form of bacterial life and not a complex life, because we only have one example happening once on Earth where photosynthesis kicked in. I think there are papers speculating on other forms of photosynthesis, but it's not really my area, so I shouldn't go into it in too much detail. There are papers on whether the types of photosynthesis can operate around M-Dwarf stars. That was in an astrobiology special issue in 2007 by Nancy Kiang, I think. But it's interesting, but I'm not really the expert on it.
Right. So chances for complex life that can produce oxygen may be quite low compared to, say, methanogenic.
Yes, I think. Yeah.
But thank you for the review.
Thank you.